I'm going to begin because once again, this is our last lecture. Hopefully, we can have some time for a little bit of a discussion at the end. But let's continue with QET as we had it. So remember that we end up, remember what we were doing, right? The protocol that I described. This is called minimal QET, which is the simplest case where you can implement the protocol of quantum energy teleportation. And this protocol was the following. We had, in this case, a bipartite 2 qubits in the ground state of some Hamiltonian. The Hamiltonian has some local terms and some coupling terms. If you remember, the local terms proportional to sigma z, the coupling term sigma x, sigma x. We start in the ground state. Then Alice makes a measurement, in this case, very simple projective measurement on her qubit, obtains 1 bit of classical information, sends to Bob that bit. Bob uses that information to operate a controlled unitary. Those words make sense to you. I mean, you've taken quantum info, so I assume, yeah, a controlled unitary on B, controlled by the result of Alice's measurement. And we showed that Bob was able to have a negative energy cost of that operation, meaning that Bob is able to extract energy just using the information that Alice sent. So Alice actually, of course, put energy into the system, right, because the measurement cost energy, and Bob extracts energy into the system, so Bob always extracts less than Alice puts in. But the key point here is that the energy, or I want to discuss today, the energy never travels from A to B. It's not that the energy is put on A and then travels to B. Although again, for the system of 2 qubits, things are slightly more difficult to define than in the continuum limit of a QFT, where locality is guaranteed by construction in the theory. But in the sense that we know that in a coupled system, right, if you put energy in A, there will be some speed of propagation of that energy, speed of sound. Have you heard about Lieb-Robinson bounds? Okay, so you know that there's a speed of propagation through interactions of information, and in particular from energy from A to B. That speed of propagation has some finite value, and we will discuss that. This is faster. In general, this is as fast as you want, right? Because the classical channel communicating A to B doesn't have a speed limit in principle. This is a non-relativistic system. Make sense? It was couple of things were asked. One of them we will address today. Number one thing that is asked, what about the energy cost of communication? It could be 0. That's my point. It could be arbitrarily low. We discussed, remember when I had Abraham Lincoln here and I discussed that you can transmit information without transmitting energy. Anyway, you can transmit energy with as low information with as low energy cost as you want. Okay? Makes sense? All right, so today I'm going to address the question you asked, which is this just Alice putting energy and then the energy propagating to B and B getting the energy? If it were that, it would be very boring and wouldn't have a name. Wouldn't you agree? All right. So very easy. So let's discuss the natural energy cost, energy flow from A to B. It's actually important. Okay, I'm gonna show you 2 things. So a question that's extremely important here, and maybe if we had more time, we could discuss more, because this is very relevant in condensed matter in many body systems. Even more so in QFT. In QFT, it's kind of solved for you and you have to deal with it. But in many body systems, before taking a continuum limit, what does it mean to measure a local energy? Okay, this is a non-trivial question, very non-trivial. I can define, so say that I have a lattice something like that, okay? Say a lattice of harmonic oscillators, and I ask you, so okay, I give you a Hamiltonian, right? And the Hamiltonian is something like that. Say that it's periodic, just to make it even easier. And you get something like that, maybe K for fun. a system of coupled harmonic oscillators, right? And the coupling is XX, QQ. Agreed? So the question is, what is the local energy of each oscillator? What would you say? If I ask you this question, what would be your opinions? Yeah?
They're all kind of connected, so I don't know what you mean by local, I guess.
Yeah, very tough. So in QFT, what is is there a notion of local energy in QFT? Yeah, no, you get the energy density, T00. That's a notion of local energy, very well defined. What is the equivalent here? Well, I don't know. You can have, for each of them, you can have this term, and then add maybe 1/2 of the interaction with the neighbor on the right and 1/2 on the left, no? In the continued limit of that, you get a scalar, massive scalar field theory, and that becomes T00. But that is ill-defined in a way, because I can have 1/2 with the right? Sorry, 1/4 with the right and 3/4 with the left. That also has the same continued limit. Okay, so the notion of what is local energy, what are local observables, extremely interesting notion, is non-trivial. So let me just say it like that. That's it. We have two qubits here. Going back to the board for lighting purposes. Thanks a lot. I'm going to say, well, say what is the expectation value of energy at B, okay, at the qubit B. So we say, okay, first let's look at the expectation value of the local Hamiltonian of B under time evolution under the interaction that couples the two. Agreed? So let's do the projective measurement part. Let's do, so Alice measures, okay? And then we say, okay, Alice measures, and then energy is going to be put on Alice, and it's going to propagate to B. Let's look at the local observable HB. What is the expectation of HB after Alice's projects? And then you see that it has this form. This is the expectation value. Very simple. Make sense? You can tell this thing starts being 0 for 0 time. Obviously, it started in the ground state. And there's some speed of propagation. And you can tell the speed of propagation is this K. Here is the coupling strength, right? The stronger, the more rigid the spring, the faster the speed of sound. Make sense? Now you can say, well, but what about the interaction term, right? There should be some part also that belongs to the interaction. So the interaction part does not belong to A or to B. It belongs to both. So maybe in B, yeah, this is very nice. I picked my multiples of identity and everything so that in this case, it's very simple to deal with. There's no interaction exchange expectation. Make sense? So in this case, it feels a bit more reasonable, perhaps, with the caveats that I mentioned, right? To think that this certainly is giving you the local energy at B because there's no interaction term. And the other term is local on A. Make sense? Okay, so this is telling you that there's an energy flow from A to B. Of course, when A makes the measurement, the energy propagates to B. But it propagates at a finite speed, and the speed, the time it takes, the time scale associated with this energy transmission is K minus 1. Make sense? So as long as your communication channel is faster than that speed of sound, you're fine. You are not. It's not the energy coming. This is not what limits. There's no K in the communication part of QET. Yeah.
Should I think of this K inverse as a Lieb-Robinson speed, like this constant that?
Kind of, yeah. It would be definitely is the scale that gives you the Lieb-Robinson speed. Yeah. Make sense? Now, of course, this is cheaty, not really cheaty, yeah, but cheating in a way that this is not relativistic, and you can tell, of course, that for any time different from 0, that energy is non-zero, right? But it's certainly not the energy that we teleport. Make sense? All right. And now let's talk about the following, right? So imagine that someone says, okay, how important it is that Bob receives the information, right? What if Bob is some sort of daemon that can implement any unitary that he wants on B? Okay? And then the idea is that, well, if I can do whatever I want, right, then surely I should be able to extract the energy even without Alice telling me anything. Alice did something. You say, if you're thinking this is because of some notion of entanglement, collapse, Alice has, it is related to entanglement, it's related to correlations, as we said. But maybe you can think, well, this is probably because there's entanglement and Alice altered the state and then I'm able to extract here. I don't really need the information. Somebody may say, can I extract any energy if Alice doesn't reveal to me the result of the measurement? It's a very natural question to ask. Okay. So say that Bob does not know the result of Alice's measurements, but Bob is allowed to do some unitary, WB here. So this is, in a single shot case, this is the post-measurement state. So Alice projects the ground state on whatever the result of her measurement, then Bob applies this unitary. That doesn't depend on alpha. All right, then let's do it for an ensemble of identical measurements. And then what we get is indeed that what Bob is doing is applying the unitary to the post-measurement state on average. And again, you don't need to average over the WB because that thing is independent of alpha. Make sense? All right, so now we recreate the same calculation that we did before, which is what is the energy cost of implementing this W. Well, that's easy. It's the trace of rho 2 minus the trace of rho 1. The trace of rho 2 Hamiltonian, total Hamiltonian, minus the trace of rho 1 total Hamiltonian. All right, so we already know that trace of rho 1 Hamiltonian is what we call the energy cost of the projection. And the result is this. Okay. Notice that I used the fact that PA commutes with HA and W commutes with HA because W is local to B and PA is local to A. Make sense? Well, it's local to A, but it commutes. We remember that we pick the PA that commutes with HA. Make sense, everybody? Okay, so that's why there's no HA here. But notice that the only place where we are having an alpha is in the projector that is applied. And we know, of course, that the identity can be written as a spectral decomposition of all the orthogonal projectors, right? Which in this case is 2 because it's a qubit. Make sense? All right, so in that case, this just becomes that. Agreed? All right. All right, so let me recover the HA. I just wanted a simple expression, but I want it back. So, oops. This is the punchline. So I recover HA, I put it in, and I get that the energy cost of W has this form. Agreed? Okay, so if the energy cost of W has this thing, can this thing be negative? What do you think? Can we cleverly choose W? Again, you're a demon now. You have all sorts of powers, including choosing your W to whichever one is best for you. Can this become negative? That's the question we're asking, right? Whether this can become negative. Yeah.
I don't know the properties, but I mean, you're like conjugating Hamiltonian by unitary, so it feels like you should not flip the sign of the spectrum, but I don't know.
No, you do know. Unitary operation cannot change the spectrum of an operator, agreed? This Hamiltonian is bounded from below. In fact, bounded at 0. Remember, I picked my F to bound it at 0 from below. It's a Hamiltonian. So it's definitely had a ground state. It's bounded from below. And this thing would not be able to change the spectrum. I can reshuffle, I can rotate, I can change the eigenvectors, directions, but I will never be able to change the spectrum. That's the point of a unitary operator. Make sense? Therefore, this is H, we know is a non-negative operator, therefore the expectation value will always be greater or equal than 0. Therefore, this energy cost is always positive. So, if Alice never sends any information to B, even though B is a demon that can choose the W whichever way they want, well, look at that. It would not be able to extract energy. Make sense? So, yeah, go ahead.
It makes sense, but I'm also confused about the fact, what if I accidentally choose the right?
That's why we averaging over all the possible cases. On average, sometimes it may be lucky, but on average, we extract no energy.
Right, but in a single shot,
in a single shot, yeah, but in a single shot, you can get energy out of the ground state too. Like in a single shot, 100%, you can catch a fluctuation. If you're not measuring the operator age, right? If you're doing something local, of course, you can get something out. Single shots should not be considered. Single shots are noisy. We're talking about on average. Can you run an engine with this?
I see.
Make sense? The idea is that if you do an operation on the ground state, right? You can, so for example, say that you have the ground state and you do a local operation on the ground state. Sometimes you're going to catch a fluctuation up, sometimes down, but the expectation value is going to be larger than 1. You don't talk about single shots, you talk statistically. That makes sense?
What if Bob performs a random unitary channel instead of a single?
It's the same thing.
But
Convex combination of...
But if the probability distribution comes from the Alice's measurements?
Yeah, no, then yes. The idea is that Bob cannot use the information from Alice. Alice is hiding the information to Bob. If Bob can tweak the probability distribution by knowing Alice's results, 100%.
I'm trying to see where things go different. If the probability distribution comes from Alice's measurement.
Is what?
It comes from Alice's measurement.
Yeah.
In the case of random units.
Well, you would have an alpha dependence on the choice of operation. You have a probability and then distribute it over the alpha, so you cannot factor out the W alpha dependence. Yeah. Make sense, everybody? That would be less efficient. So the ideal one would be the probability delta of doing the right one. But of course, if you have a probability skewed towards that, you will get some fraction of the energy. That makes sense? Do we understand the minimal QET model with 2 qubits? Okay. Any questions? Yeah.
Can you comment? I know in the Bell's inequality there's this no signaling condition, and here it seems like it's the opposite. It's like yes signaling condition.
Yeah.
Is there any sort of like connection to the Bell inequality from this perspective, or I don't know?
I don't know. So the idea, if we understand this this protocol, so if I ask you to rate this protocol from 1 to 5, what would you give it? So it's very simple and it's deceivingly simple. It's his implications are deeper, but what you've seen, what would be your rate?
4.
A 4, very nice. For me, it would be a 5, but I'm biased. Okay, the idea here being that locally, right, you are acting on something that looks like the ground state. And there's nothing, imagine that the information travels faster than the speed of sound. There's nothing around you that tells you you're not in the ground state. If you were to tomographically probe your local state, it would look like the ground state. You say, oh, I'm in the ground state. And yet, to something that looks like the ground state, I'm extracting energy out of it. With no energy traveling from A to B. That's the key. Those are the key ingredients I want to put in there. Yeah.
It does seem like if we are only using the system to communicate, we would be bound by the speed of sound on the system.
We'll get there.
So it seems like we need to have an additional environment where our photon of information can propagate or something like that.
Yeah.
So it has to be decoupled from the system.
Not necessarily.
Okay.
But we will discuss that. But in principle, yes. So the answer would be yes for what I presented. Yeah.
We need to somehow beat the Lieb-Robinson bound. Was that okay?
Yeah. In principle, we will see a case. We will see QET in a massless field for something cool, and there, of course, you cannot really communicate faster than the speed of propagation of the perturbation in a massless field. With a massive field, yes, you can have a massive field and then a massless field, 2 fields, one to communicate, one to do QET, for example. Make sense? All right. So this is Masahiro Hota, by the way, and this is they did a very nice. Charlie Wood is a cool guy in terms of shout out to Charlie. He took a lot of care to write this article. When we did I'll explain that. When the experiment was done, Charlie reached out and wrote this article about it. And he was extreme, you know how, I don't know how many, but you'll find out when your research goes to popular science, which happens, right? When you do something that is deemed as cool by whoever, they usually twist everything. It's really a fight, it's a struggle, it's a horrible struggle. No matter how good they are, even at Nature, when they do these reviews at Nature of papers, they destroy them too. Okay, so, but Charlie Wood is my best experience doing a popular science article of actual research. So he wrote this very nice, of course you have to put the headline there, right? But to the clickbaity stuff. But he did an extremely great job. So I recommend actually that article. This one came, so we'll talk more about it, right? But the experiment that came out of this was actually Quantum Magazine chose it one of the biggest breakthroughs in physics of 2023, which is nice. And Charlie did, once again, I recommend you read it, it's kind of cool. Anyway, so that's Masahiro Hota. This is Masahiro's handwriting. I asked him to, how do you say quantum vacuum in Japanese? And he wrote quantum vacuum. That's the quantum, and there's the vacuum. All right. It's kind of interesting, right? Because this is the unit of. But in Chinese and Japanese, this is the unit of. So to say photon, you say unit of light or quantum of light. To say electron, unit of electricity. It's kind of cool how they do it. Quantum is just kind of like an atom or unit of matter kind of thing. That's what it means. Anyway, let's talk a bit about thermodynamics. All right, so because this is actually to try to understand what QET is doing, we need to talk in terms of thermodynamics here. How familiar are you with quantum thermo? Have you seen any quantum thermo at all in your PSI courses? Probably not. A little bit? Okay. So, passivity. Thermal states, for example, are passive. What is the definition of a passive state? Well, for any arbitrary unitaries, you cannot extract, on average, any energy. That's the definition of passivity. Makes sense? It connects with the second law of thermodynamics. In a way, it's a quantum reformulation on the averages of the second law of thermodynamics. In fact, if you do non-equilibrium thermodynamics, it's literally the translation of classically would be the same definition. On average, there's no passive states are those on average where you cannot extract any energy from them. Make sense? In a closed operation, non open. In particular, passivity implies local passivity, which means the definition of local passivity is as non-trivial, the local part, as that stuff. Okay, so we'll talk about what I mean by local here. In particular, if you apply operations, say, that only involve observables in a lattice, in a many-body system, only involve observables associated with one element of the lattice, that also would not be able to extract an energy. Makes sense. So passivity implies local passivity. Make sense? All right. So this is about unitaries, right? But what if I allow CPTP maps in general? So I have a passive state, but I'm no longer considering a closed system. I'm allowing to have an environment or something that is non-unitary. Okay. What if I do something, right? For example, I have the temperature of the system to be larger than the temperature of some ancilla, and I couple the ancilla to the system. And the idea is, well, if you wait long enough, well, there would be some energy flow from the system to the ancilla, no? So the question is this local? Is this operation local, even though you're touching one of the ancilla? But again, once again, the word local is extremely misleading and has 4 different meanings, 2 of them relevant for this course, or maybe 3. The idea here is that, well, usually it's a non-local process in the sense that for this to happen, to establish a thermal flow in the sense of the zero law, you need to wait for enough time that the whole system knows about you. You would never thermalize with something unless you let the whole phase space of your system you're thermalizing with to know that you're there. Like if I talk with the corner of the table and I say, hey, I'm here. The corner of the table says, wait, I need to talk with my friends and we'll decide what to do. Make sense? So it involves, there is information flows that involve the whole system in the thermalization process. Make sense? So calling it local could be misleading. This is Masahiro Hota's hand. It's not really his hand. Well, it is, but the meaning is not. This is a hand he used in a presentation, and I copied that hand. So it's technically his hand. Let's say that I have a hand that is colder than the system. And I'm gonna let the hand touch the system. Say that this is the sun, right? Something hot, something very hot. Think of the sun. Question is, will the hand get burnt or not? Well, now if you touch the sun and you keep it there, yes, you're gonna get burnt. But the answer is not in general, right? In the case that you have, so you can prove. So think of this: if the ground state. So say that I do a local CPTP map, meaning that I don't wait, I just touch it very fast. Okay, to try to mimic a notion of locality here. Touch it very fast. If you touch it very fast, you may not get burnt. Okay. In fact, if the ground state of the system contains max rank entanglement, max rank means that this mixed decomposition is full rank. Okay, it's not about the amount of entanglement. It's about how distributed across the Hilbert space the entanglement is, if you want. Then there exists a temperature T star under which it's not possible to extract work from the system through any local CPTP map. Meaning that there is a temperature under which, if I touch it locally, I'm always going to put energy into it, not extract. So the first theorem was for 2 qubits, was 2013. Then there's a theorem for more general systems in 2014. And the most general one, I should actually show you the review. I'll show you the review at the end. I'm going to do this is from a presentation, so I'm sorry, but I'm going to show you some pictures. But these are the people. So there's Nayeli, former student of mine. Jane Sikora down here, Giorgio Stellare is there, and Alvaro Martin Alhambra over there. And those are the people. Alvaro used to be here, by the way, as a postdoc. And Nayeli too, she was my student, and Ray LaFlamme student as well. And in 2019, we generalized this. We did the most general. Okay, those are the sufficient conditions. We have necessary and sufficient conditions in that paper, which is, we feel very, very happy about that. We don't have to go through the theorem. We don't have enough time, but there is a theorem, and I'll show you a review at the end that talks about all this. But the idea here is that in general, if you have a hot system at a temperature lower than T star, then you touch it, you are going to input energy into the system, not extract. And let's call this strong local passivity. Okay? Makes sense? Strong. So local because it's just a fast touch to one of the subsystems. Strong because it's on any kind of operation, not just unitaries. Yes?
If you treat the external system as its own separate system, and that's like a local interaction to the external system too, would this not imply that it also transfers heat from the external system to the, like, it feels like if you're saying that, like, it gets transferred one direction specifically when the setup is, like, symmetric, like you have a system here, do a quick local interaction. Like, it feels like, on average, there should be, like, no net energy flow.
Yeah. So zero is also a possibility. Yeah.
Okay, sure.
In general, is what you prove is that what cannot happen is that you extract energy from the system.
Okay.
It could happen that there's zero exchange, yes.
But like, wouldn't proving that no energy extraction can happen also imply that no energy deposition can happen? Because they're both like...
You cannot prove that. So in general, you're gonna get energy input. There are cases where it would be zero energy flow. Not sure I understand.
I guess I'm just thinking, like, what if the hand is also a quantum system that behaves exactly the same way?
Then this is zero in that case. But in that specific case.
Okay, so we're not necessarily considering the hand actually being a quantum system that's doing a local...
No, the hand, this is a CPTP. So the idea here is that doing a CPTP map on B would not be able to extract energy. You can think of that CPTP map as being the result of touching it with some other system.
Okay, cool. Thanks.
Makes sense? Also, the other system may not be in a thermal state.
Right.
The other system may be in a thermal state above the it may not have max rank entanglement, like
Okay, that makes sense.
may not be. If it's identical, if both are strong local passive, then the answer is 0 energy flow. Yeah.
Right, that makes sense.
All right, good. So we can think of QET as breaking strong local passivity is a way, but you see, the strong local passivity, you have to break something. It's a theorem in order to extract energy. Let's break strong local passivity by adding LOCC. So you see, strong local passivity talks about local operations, but no classical communication. So here we're going to add the CC part, and the CC part breaks strong local passivity, and that's what's behind QET. We already saw this in more detail even. Let me talk about, because I thought it would be cool. Have you heard algorithmic cooling, these words before? It's very sad that you haven't. Not sad as in a bad way, but I wish you had. It's very cool. Imagine you have a fridge, okay? This not regular fridge, not a sentient one like this one. So imagine you have a regular fridge. And then I ask you, here's a bunch of qubits. I want to cool down some of them. Why? Because I want to do maybe quantum information, quantum computing tasks with it, right? So I need pure states. So I need to cool them down. Make sense? And imagine, or imagine that whatever, you want to have a drink and the drink is very hot and you want to cool it down. And say that inside the fridge is 4 degrees, okay? And then I ask, somebody says, oh yes, put it in the fridge, and you take it out after a while. And you say, yeah, no, but the fridge is 4 degrees, and I want it at 0 degrees. What would be your answer? What would you? Can you do that with your fridge that is only as cold as 4? Yeah.
Naively, no, but I would say naively, no.
Naively, no, but you know more?
I was thinking for like these, how do you call it, superconducting qubits. They have these fridges which are at 4 Kelvin or something like that, but they do some magic with different kinds of heliums.
Okay, but that's different. That is a better fridge.
Right.
That is not, you only have your resource theory here. Your resource is, you have the fridge, and you cannot spend in a better fridge. You cannot have laser cooling and then, do evaporative cooling. No, you can't do that, okay? You just have your fridge. And the idea is I have a thermal reservoir and I want to cool something below the temperature of the thermal reservoir. That's what I want to do. Make sense? All right. Create tuna jelly for the animations here. All right, so this is your fridge. This is your thermal reservoir, or a sample of it. Thermal reservoir technically is infinitely large, as per definition of a thermal reservoir, much bigger than the system you're cooling. And I have a bunch of qubits here, say qubits of quantum systems here, okay? And I want to cool down, say, this one, okay? Of course, what you can do is you can put this one in the fridge and take it out, and it would be as cold as the fridge. Makes sense if you let it thermalize. However, here's another trick. What if I apply a unitary on my system that compresses the entropy? What is that? It plays with the entanglement in the system so that I purify as much as possible qubit number 1 and I make as mixed as possible the last qubit. We call that entropy compression. We put all the entropy in one of the subsystems. Make sense? That's the unitary operation. If I do that, now I can cool that. I call that the reset qubit. Let me call the first one the target qubit. And now I'm going to thermalize with the reservoir the reset qubit. Make sense? And now what can I do? Well, I can do entropy compression again and put all the entropy as much as possible back to the last one. Make sense? And now I repeat. And if you repeat, there's a limit, but you can tell already that by doing that, you have cooled down the first one below the temperature of the fridge, of the reservoir. Make sense? Yeah.
Why would it be below the temperature of the fridge?
Because you have put, well, in general it's below. So you have all those, right? And then I put this one, the last one is hotter. So you are dumping more entropy. So think of it in entropy flows. There's a lot of entropy here, more than there was before. So I dumped all that entropy into here. The idea is make it more efficient, the exchange of entropy. Yes?
How is this different than like just a regular heat engine where like you put a bunch of hot into the gas, cool it down, and then like do that over and over?
It's one that actually, it's equivalent to that if you can use and manipulate the microscopic entropy of your constituents and you put selectively some of them. The difference is that I can manipulate the entropy distribution.
Okay.
So I can make one of my qubits hotter than the rest.
Okay.
And I do that by reshuffling entanglement in my qubits.
Okay.
Make sense? All right. Anyhow, algorithmic cooling can actually cool down below the temperature of the reservoir. And in fact, is suggested and has been suggested as, yeah, it's a better way. In a way, it's manipulated information to cool more efficiently. You can actually get lower than the temperature of the reservoir that you have for the qubits that you want to use. Yes?
Has it been experimentally verified?
Yeah,
Okay.
indeed. But then, for example, I mean, I'm going to be very fast on that because time is running out. The idea is this is very, for ideal cases where your qubits are not interactive and so on, that's okay. But what if you want to cool an interacting system, right? You can cool down the system. The ground state is entangled when you cool down the system. If I have an interactive system and I cool it down, I'm going to have the ground state have an entanglement. If I look at one individual element, one individual qubit of that chain, that's going to be hot in the sense of non-zero entropy because there's entanglement. So the partial state will be mixed. Makes sense? So the idea here is that cooling interacting system is tough. And let me just say quickly, this is a work we did with Nayeli, with Achim and Ray. You see that tank there, that thing there? This will play a role later. Anyway, the message, and I'm not going to get there now because I'm going to talk about, is that you can actually do better than the regular PPA, the regular algorithms of algorithmic cooling by using QET. You can use QET as a way to dump entropy as well, not just to extract energy. Okay, so to establish entropy flows. Let me talk first about the experimental test, and I want to end with the QFT implications of QET. I'll be relatively fast. I say that we did this experiment. It's not impressed. This is so old. It's been published since 2023. Sorry about that. I'm very bad at updating things. When I say we did the experiment, the we means this guy did the experiment. He's the guy who was working with that tank over there. That's an evaporative fridge and a superconductor magnet, and it's a nuclear magnetic resonance experiment here. And the experiment was done, let me tell you very quickly, in that molecule. It's called transcrotonic acid. The nice thing about doing this, it's actually published in 2022, not 2023, is in nuclear magnetic resonance is that you have full control. Nuclear magnetic resonance is great. You can have a molecule and you can control everything in the molecule. You can implement any unitaries, establish any Hamiltonians. It's really cool like that. You cannot scale up a lot. You are limited by the size of your controllable molecule. So not a great platform for quantum computers, but it's a great platform for small calculations or quantum dynamics, you know. So the idea here is of this molecule, we use A and B as the molecules, as Alice and Bob qubits. Okay, that's the nucleus actually of the spin, the nuclear spin of A and B as the qubits that I'm going to do QET with. And this C2 is the one that's going to establish the channel. So you can establish this Hamiltonian here between A and B and have the ancilla not have any energy. So the ancilla cannot do energy exchanges with the system. Anyway, you do the experiment, and this is kind of cool, huh? There are three. Okay, I just want to tell you that there are three curves here. The one that I computed, but I mean Nayeli. All right, that was let's give credit where credit is due. I proposed the idea, and I also did all the theory of the idea, but the calculations is Nayeli, and the experiment is Hemant and Ray, right? So anyway, that's kind of cool. This is my calculation. The ideal scenario is the red one. This is my calculation, but now implemented in a computer that puts the noise in. So it's still math, but with models of open quantum dynamics, because this is not perfect. Your implementation of your unitaries is not perfect, and there's noise coming from different things. And the blue are the experimental points. When something like that happens, I feel great. Like I did, normally your theory calculations, you don't expect them to coincide in any way with the experimental results. Now, the cool thing though is that the experimental dots are all negative energy. So the energy cost of the operation in Bob that you can measure, in fact, this is measured, is negative. And then you can wonder, is this QET or is this natural propagation of energy? Well, that's kind of very nice because you see the total experiment duration being super conservative. So the pulse duration, the pulse that implements the actions is just this long, but being very fair from the beginning to the end. So from the preparation to the measurement, this is the time of the experiment. And this is to be compared with the energy, the speed of sound in the molecule, and the speed, the coupling strength between the different parts of the molecule. So the energy propagation time scale is 1 second. The experiment was about 100 times faster. So this is not natural energy flow. This is QET, and this was the first QET experiment, and it was considered as the experimental proof of QET, which is very nice. Yeah.
So, how does C3 like know about information propagating from C1? Like, what is the
The Ancilla implements it.
Oh, the Ancilla.
Yeah. The measurement, what you do is there is an equivalence between a PVM and you can replace the classical communication bit with quantum communication bit. And this is the quantum communication bit. So this guy extracts information from here and gives it to this guy.
I see.
All right? You have to be careful that the Ancilla doesn't take any energy from the system. That's the only thing to be careful with. Make sense? Just information. All right. Okay, the idea, let's talk. I'm going to go fast. This is my former student, Nicolas Funay, now in Australia. Going very fast. You know all this. You know about energy conditions. I assume you've seen energy. I know that one of you has at least seen energy conditions, but the rest probably in your GR course here, right? Have the mottos here of the energy conditions, like there's no such thing as negative energy. That's the weak, strong, gravity is only attractive. Dominant energy must not flow faster than light, with a caveat, right? This is the flow in the sense of the time-like flow of T mu nu. Positive null flow of stress energy. Positive null flow of stress energy. Yeah, this one is the null is a bit more difficult to interpret in simple words. But we all know, right, that the null is the one that dominates all of them, and then the weak is at least the minimal one that you want if you have to have some sense in your spacetime. You know about that, the chronological censorship conjecture by Hawking. Are you familiar with all that or not? The idea here is that why do we introduce these conditions don't come from GR, they're external to GR, and they were initially introduced as way to make sense of GR produces monsters. Agreed? There are some solutions to the field equations that are really horrible and shouldn't be physical. For example, Kerr. A Kerr black hole is extremely unphysical. Do we agree? There's two horizons. Inside the two horizons, you have closed time-like curves. Not very physical. Closed time-like curves, a time machine. Not very physical. Some solutions have naked singularities. You have solutions like the warp drive. You can have, with two warp drives, you can establish a closed time-like curve as well and have a time machine. Things like that. Things that don't lend themselves to well-posed Cauchy problems, that they break the global hyperbolicity of spacetime. To prevent those things from existing, a set of conditions were devised saying, okay, under what conditions can we do reasonable GR? This is external, this is human, this is us. We don't like the fact that GR is weird. Let's impose some things to make sense. Make it make sense, right? And the idea is that with the null, you're safe. With the weak, you're not safe, but I conjecture you're safe. That's the idea. Not me, but other people conjecture. That makes sense. We know, you know about the Gödel spacetime? The Gödel spacetime satisfies, you have this, you can satisfy the weak condition and still have it as a solution. But it's a bit weird. It contains closed time-like curves, by the way. So you can time travel there. Spacetime with ergo regions, you should be careful with them. It's likely that if there's an ergo region, maybe there's a chance that there's something hiding that is closed time-like curve. If you ergo region too much, you're going to ergo region too much. If ergo region is an area where you cannot remain stationary, okay? Meaning that you're going to be dragged. There's frame dragging, extreme frame dragging. You can't avoid being dragged. If you drag too much, your for velocity may become space-like. You're gonna you can establish a closed time-like curve in those cases. So you don't want that to happen, right? That happens in Kerr, by the way, between the two horizons, okay? Anyway, so with weak, what we say is with weak together with a very reasonable conjecture, you are happy. So we tend to believe we're happy with the weak. And the weak tells you there's no such thing as negative energy for anybody, meaning that the 0,0 component of T mu nu as seen by anybody that can move time-likely has to be positive. Make sense? No negative energy density. Cool. If violated, you can get a warp drive, for example, and many other things. But we know that quantum fields violate the weak energy condition. For example, here's a very kind of cool inequality. This psi is a time-like vector. You can have that if you have a scalar field, you can prove bounds for T mu nu, and you can prove that those bounds are actually below 0. So you can get negative stress energy densities in QFT, at least on average. Make sense? So they violate the energy conditions. We can have exotic spacetime. So the idea here is to try to use QET as a way to force this to the extreme, to try to create T mu nus that are as exotic as possible in terms of violating the conditions. Still, it's a physical protocol that you can do. Very easy to implement. It's not an accelerated mirror to relativistic speed. This is just local operations in the field. So can we use QET to force a violation of the energy conditions as strong as possible? Remember, if you are in the ground state of the field and you're extracting energy somewhere, the energy density is going to decrease. Energy has to be conserved. Energy flows have to be conserved. The divergence of T mu nu is 0. So if you are extracting here, you're going to create some bump of negative energy somewhere. This is the original paper that Masahiro Hota put out in 2008. This is as old as QET. This is the first paper on QET. And what Masahiro did is a one-dimensional 1+1 scalar, massless scalar field. Masahiro and I, when we do that, we're going to use particle detectors. So if I had more time, I would show you, because now you prepare to the calculation, which is kind of cool for the local measurements. But sadly, I'm going to just be fast. Masahiro coupled a particle detector to only left movers. Okay, you see that we decouple the transmission of information towards the right from the propagation of energy that's going to be towards the left. Because if Masahiro measures by coupling a detector only to left movers here, what's going to happen to the energy? Yeah, go ahead.
So, but what does it mean to couple only to the left movers? Because left
the K of the distribution of frequencies that you have is only negative Ks.
But I thought the left versus right movers is an intrinsic choice that we make that comes from the how do you call it, the J that we put.
Yeah. Think of the Minkowski vacuum. We've already picked a J. We have Minkowski vacuum. And now I get a detector that only coupled to left movers in the plane waves associated with the complex structure of that vacuum. Make sense? You can do it in 1+1 demassless. You cannot do it outside of that. There's some symmetry, but in 1+1 you can do it. In higher dimensions you can skew towards one direction, but never fully decouple from the rest. So yeah, the energy, so you created, what I'm plotting here is T00, according to these observers. So Alice couples creates a positive energy bump. The energy bump moves to the left. You have another lecture, no, after mine, I assume. At what time?
11:30.
Yeah. Okay, moves towards the left. But then Alice sends information to Bob. Bob performs, this is not accurate representation, but Bob performs some operation, and the expectation is that if you do QET in this case, then Bob is going to be able to create some negative energy there. Make sense? All right. Now, if you want to do it realistically, you cannot really couple realistically to only left movers. If you want to do an actual experiment, you're going to be coupling to both. So you have something more like this. So the blue dot here represents the information transmission. Okay? So as you couple, the information and the perturbation, they both travel at the speed of light. Make sense? So it's not only that Bob is going to have to create some negative energy density around him when it was the vacuum. It's a bit worse because it has to create some negative energy density overcoming the positive one that was sent by the perturbation. Make sense? It's a bit more difficult. Okay, we're going to do, the protocol is going to be like this. Alice has an atom, a particle detector, that couplings, or maybe a cloud of them, she couples at some point. Then Alice measures the non-relativistic atom, as we said. Remember, you cannot do a PVM on the field, but you can in the atoms, right? So you measure those atoms. You broadcast the result of the measurement to an agency of Bob's. And then Bob's agents use that information to prepare the atoms, a cloud of atoms, say around Alice, and coupling those to the field. Make sense? That's the protocol. So this means that I'm going to first do a toy model in 1 plus 1D, and then we'll do the 3 plus 1D. Okay. All right, so here I'm going to replace the classical communication by quantum communication for simplicity. So instead of doing the measurement on Alice and then sending the classical information to Bob, Bob preparing the detectors like that, I'm going to just teleport using regular quantum teleportation the state of Alice to Bob. Make sense? All right, so say that Alice and Bob, they share an entangled couple of detectors, and then Alice couples one of them, and then uses quantum teleportation, sending classical information to send it to Bob. I'm going to skip a bit the details, but then you can tell that after the whole protocol, you end up with something like this. It's kind of cool, right? Because you get Alice's contribution to the energy density because she coupled. You have Bob's energy contribution because Bob coupled. These things are positive. So the effect of coupling the detector generates positive energy in both cases. But then you have these terms that are related to the correlations between them. And then you look at these terms and are like, okay, it's kind of exponentially suppressed with some scale. But this guy, the sign of this guy is going to depend on the initial state that you choose of the qubits. Agreed? Which is the same as what observable you measure or what observable you're coupling. You can put the freedom of choosing the observable on the initial state of the qubit. So the idea is, can you make these guys negative? And the answer is, well, you can. Can you do them negative enough? So let's just see what happens. So let's consider that Alice has a Lorentzian cloud of detectors. She couples to the field. She couples to the momentum of the field in this case. So you're gonna have the derivative of the Lorentzian here, which is what you're seeing here. That's the energy density immediately after Alice coupling. So Alice dumped energy into the field. Of course, after some time, it propagates. And now it reaches the position of Bob. Bob is sitting here. Okay? Now Bob is going to couple his detectors now. So after Bob couples his detector, this happens. What happened there? You saw what happened? Bob dumped a bunch of energy into the field as well. That's unavoidable. Agreed? Because of the coupling, Bob also dumped some energy into the field. But let's let it settle. Now Bob, part of it is going to go to the left, part is going to go to the right as well. This is what happens afterwards. So you get a left propagating positive energy bump, and that is larger. And then you have a right propagating energy bump that has this peak here, negative energy density. So far, so good. So yeah, you can create this. Notice, hopefully we have time to discuss it, that this negative energy bump is surrounded by positive energy. Okay, let's do the actual 3D 3+1D case. So you have several. So there's no gravity in 1+1D. So if you want to do exotic spacetime stuff, you better do it in 3+1D. Okay. There's no gravity in 1+1D. Gravity is boring in 2+1D. Gravity is quantizable fully in 2+1D. Gravity is real in 3+1D. Okay, tidal forces and all the cool stuff, propagating degrees of freedom of. So 3+1D is the way to go. Several complications. You need a gas of Alice and Bob's, and the main reason is that you cannot do the trick that I did before. Before I used quantum teleportation, assuming that it's only 1 degree of freedom for Alice and 1 detector for Alice, 1 detector for Bob, distributed with a smearing. Cannot do that here. You have a cloud of them, so you cannot teleport the state of one to the other because you cannot teleport the state of one detector to many. And of course, it's just more mathematically more complicated, right? So once again, what we do here is once again use some mathematical tricks of taking the continuum limit of a gas distribution and writing an effective macroscopic detector out of the many, the cloud of the many. Don't have the time for the technical bits, and then also use the equivalence of LOQC and LOCC in some cases, but in the end you end up with something like this that looks a lot like before, only the expressions are very complicated, like these guys are quite complicated integrals, this size, irrelevant. So here we have Alice that has a Gaussian distribution of atoms centered at 0. Okay, cloud. And then Bob has a ring of atoms surrounding Alice at around 17. This is Nico. So Nico loves non-round numbers. He loves that. So you have to, some people may ask, why not 15 or 20? Well, that's Nico, not me. Okay. All right. I think it's actually 16.5 or something like that. But anyway, so you see the picture, right? This is a section. This is a projection to a plane from above, the center cloud, and then a ring around. Okay. Cool. So switching on time. So let's say Alice does her operation, and of course what you get is some mode that propagates outwards, some modes that propagate inwards, but the inward mode is reflected by the center, obviously. So in the end, you have this thing traveling outwards. Okay, so this is the energy distribution that you see traveling outwards. And then it reaches Bob. Now Bob is going to couple his cloud of detectors. That happened. Look at that squiggle there. And then we propagate. We let it propagate. Some part goes inwards, some parts go outwards. So you see the little smidge here of negative energy. We can zoom in a bit. Look at that. How proud would you be of that? Looks like nothing, no? Looks small. Well, you have to take into account that we're in 3 dimensions. So you have the area law spread. Things propagate of everything. So there's a surface, if you want a ring of negative energy surrounded by positive energy. But then you can ask, what is the amount of negative energy that you can put in there? And let me say, you can put as much as you want, as long as you make your cloud more dense. You can scale your system, making the cloud more dense and the coupling stronger, to as much as you want. And you can prove, and we do prove, that it violates the energy conditions that I show at the beginning optimally, and also saturates the quantum interest conjecture. I don't know if you heard about what the quantum interest conjecture. The quantum interest conjecture tells you, yeah, with QFT you can put negative energy density into a field. However, obviously there's a limit on how much, right? In order to put E, negative energy, you have to create positive E, negative energy somewhere else. Because if you're in the ground state, right, with energy 0, you cannot have less energy than the ground state. When you integrate the stress energy density over the whole of a Cauchy surface, right, you need to have a total energy being at least the same or more, right? The quantum interest conjecture tells you that you need a bit more. It's not just the same amount, you need a bit more. It's a theorem in 3+1 flat, by the way. It's a conjecture in general. But the idea is that you cannot just create as much negative energy as positive. You always have to pay an interest and the interest is gonna have to accompany you as well. You can always have negative energy as much as you want, as long as you have some accompanying positive energy to it that propagates together. Okay, that's the quantum interest conjecture. So we can prove that this protocol, QET, saturates, it violates, you can do custom-made violations of the weak energy condition, as customized as you want, scaling optimally, or as optimally as the law of physics allow you. And I'm not going to talk more about it because I want to discuss. The idea now, of course, is that if you use this, can you create an energy density distribution that is supposed to feed an exotic spacetime? Can I create a warp drive T mu nu? The answer is yes, you can, in flat spacetime. What is not studied yet, and I wanted to show this. The one thing that is not clear is if spacetime likes it while you do it. So one thing is to say, I have a curved spacetime, so a flat spacetime, and I create a negative energy distribution. That is the one that I get from the warp drive. If I have a warp drive spacetime, I can compute the right-hand side of T mu nu, of the Einstein equation, and say, what's the T mu nu that fits that? Another thing is I dynamically create this T mu nu. Is spacetime going to curve the way I want it? This is not studied yet. You can't imagine how difficult it is to do numerical relativity when you drive with a quantum source, with a quantum field. I would imagine, when I started doing that, I might know this is probably done. The people in numerical relativity, in strong gravity, as they call it here too, probably would have solved this already, done it many times. Not really, no. They usually drive things with classical fields. So quantum fields driving, not even in semi-classical. So it's a difficult thing. But it's to be explored. In principle, you can use QET. What I want to tell you is that QET is very functional. You can do it. So it may be, of course, you need clouds of atoms that you need to address individually and so on and put them in space-time and all that stuff, right? But this is an engineering problem now. It's not a science problem. Accelerating a mirror to relativistic speed is a physics problem. You cannot. There's no material that would ever do that. You cannot accelerate to the speed of light in a reasonable time, a mirror, and then still behave like a mirror. This is an engineering problem now. The physics is, we know, I told you, find your favorite atoms, the most controllable ones, and do this protocol. Problem is, of course, addressing the individual ones and so on, but look, maybe a problem that can be solved in a century, and then you can do it. The people in neutral atoms are you following that? What people can do with neutral atoms these days? It's mind-blowing, it's crazy. It's crazy. They can implement, if you had gone to Cheyenne's talk maybe, but it can implement non-local gates among many qubits by just displacing, because neutral atoms you can control with optical tweezers, so you can move them, you can manipulate it, you can put them wherever you want. Great promising platform. Have you heard Google talking about it? Google has talked about it. Google said, neutral atoms, we're going to do two things. Warn the world that maybe a relatively powerful quantum computer can appear at some time soon, the next 10 years or so. Maybe, again, you know the costs of building a quantum computer scale exponentially with the size. It's not a matter of physics now, it's a matter of economy if you want. The second is we're going to hire the best people doing neutral atoms. So they're serious about it. So neutral atoms is an extremely powerful platform. So I don't know, maybe this is something that in the future you can use. You can force relativity to regimes relativity has never been tested. So maybe there's quantum gravity coming out of that. Why? Because, I'm forcing GR to give me exotic solutions when I drive it with quantum matter. Maybe semi-classical gravity fails completely. Maybe you predict one thing, you do the experiment, and you don't get the exotic spacetime. You get something else. That something else is not GR. One of the holy grail of experimental gravity now is finding a case that cannot be explained with Einstein equations or semi-classical gravity. If you find that, that's cool. Because maybe it's not quantum gravity, but at least it's not GR. We're on the right path, right? Okay, this might be one of those things. Yeah.
In the atom example with the sphere of atoms, those are detectors, so they're treated as classical objects, right?
No, they're quantum detectors.
But
like the ones that I introduced in class, particle detectors.
But still quantum mechanical objects.
Yeah, not relativistic, internally.
Yes. And then when you say quantum field that couples to these detectors, what quantum field would be in that example? Like
the electromagnetic field,
electromagnetic field,
for example. Well, I did it with a scalar here, but it cost me nothing to do it. Nothing. It cost me an appendix of 20 pages to do with the electromagnetic field with a lot of 3J symbols, but that's all.
I see.
You know what I mean? Like, it's a matter of algebra to do it with the electromagnetic field. It's a vector field, a polarization, and you have completion relations between the projections on the polarization space and so on. Yeah.
Throughout all of this, it seems like we've been assuming that gravity couples to the normal ordered expectation of the stress energy tensor.
Indeed.
Do we have any indication that is reasonable? Or?
I would say that when you have the vacuum, we don't detect any curvature of space-time.
Okay.
That is the only thing I can tell you about it. Meaning, like, I'm going to normalize the energy origin by what I observe. I observe Minkowski when the vacuum is when the field is in the vacuum. But more than that, it's a reasonable one. I wouldn't say it's unreasonable, but it's certainly an assumption. Yeah.
Okay.
So we're done. I would have liked to have today's lecture. On Wednesday we usually have 2. In my mind, for a long time, we had 2 today. We don't. I would have liked a discussion session. So Irene is here, which is nice. I'm gonna ask Irene to maybe coordinate with you for when I'm back by late May, and we can have one session for those of you who want to have a discussion and brainstorming on this. Also, we'll give you time to think about all this stuff. You're gonna do the tutorial today is gonna be about QET. You're gonna relax the 2 qubits thing. We're gonna do a chain of harmonic oscillators, and we're gonna relax the PVM part. You're gonna do POVMs in general. These are the 2 things that you're gonna do, and you're gonna look at QET in those cases. Other than that, the second homework is already sent or not? Yeah, perfect. You got the second homework? No? It's on David's desk then?
It will be sent to the other.
Okay, but you haven't sent it to David yet.
I have.
You have. Okay. Anyway, other than that, it was great to do this. You were a little bit guinea pigs of the new structure, trying to put more content based on the book. I think your feedback is extremely helpful. If you want to tell me things that you would like to improve, or things that you that you liked, these kinds of things for the next time. I hope you learned some things. At the very least, you've seen things in a different optics that you usually do. At least like the QFT part, I'm pretty sure that you haven't seen these things before, or at least not in the way that I did it. And I hope that now I put in them on the map for you relativistic quantum information as a cool field that asks cool questions for cool answers. Consider that in the future. Other than that, well, again, I'll see you late May, those of you who want, and then we can have some discussion. Think about all the topics, prepare questions. It could be fun. Let's have a fun, relaxed, unrecorded session. All right, cool. Thank you.